research talk, but I hope that it will be useful to everyone. Right, so I've just switched the slide to slide 2. If you don't see it, please let me know. I will still introduce myself and San Jose State U. Then I will first talk about the basics of quantum computing, in case you are not aware of them, during which I will talk about the basics of error correction also. And then based on what we learned there, we'll further look at how a quantum computer works with its hardware. We'll look at silicon qubit and also superconducting qubit. And I will also show that how we use your tool, HFSS, to do the design, right? Probably you know much better than me. We're just the user. And I will also talk about the cryogenic electronics part, because a quantum computer is nothing but just some passive qubit controlled by very sophisticated microwave electronics. In particular, I have a new book on quantum computing architecture and hardware for engineers. So I kind of learned this with, of course, with some mentor, learned this by myself. So as an electrical engineer, I know what are the barriers. So I try to do it step by step, and it will be available in January. And these are the table of content. And today's talk is actually based on this book, 10,000 Feet Overview. Okay, so let's go ahead to talk about the basics of quantum computing. Some of you probably know already, but anyway, a quantum computing, unlike the classical bit, we store in 0 and 1. In quantum computer, we store it as a superposition of 0 and 1, and people usually represent the states on this broad sphere. So for 1 qubit, it is a superposition of 0 and 1, A0 plus B1, and it can be any point on the surface of this broad sphere. So in quantum computing, all we are trying to do is apply the quantum gate to rotate the qubits on this broad sphere. But this quantum gate is not we know about in the silicon IC, right? Traditional IC. A gate is usually just a laser pulse and microwave pulse. This is going to generate a Hamiltonian, an energy landscape for the qubit that's interacting with them. We will see that later, right? So we need to have 1 qubit gate, which means it operates on 1 qubit or 2 qubit gates. And most of them have classical counterparts, some does not have, because one of the important things in quantum computing is superposition. So some gates will make a 0 state to a superposition of 0 and 1 state, for example, the Hadamard gate. I want to talk about this 2 qubit gates a little bit, right? This is something called entanglement gates. There are many different entanglement gates, but they're essential for quantum computing. We just say that superposition is important, and quantum computer is important because they can also form entanglement. We won't discuss the detail, but I do want to discuss the detail of the CNOT gates or exclusive OR gates here. So what does it do? If you apply to 2 qubit, right, A and B, there's the 2 qubit, it can be 0, 0, 0, 1, 1, 0, 1, 1, right? So this is 2 qubit, they are the basis states. Of course, you can have a superposition of them, which we'll look at it later. Control NOT gate is just that you have 2 qubits. The first one we call it control qubit. The second qubit is the target qubit. And the control, when you apply to this 2 qubit, it's going to do a NOT operation or exclusive operation. But let's just treat it as a NOT operation. If the first qubit is 1, for example, this 0, 0, then it's not going to do anything. So it is still 0, 1 becomes 0, 1. So 0, 0 becomes 0, 0, 0, 1 becomes 0, 1. But if the first qubit is 1, then it's going to apply a NOT operation to it. So 1, 0 will become 1, 1 because it negates the second qubit. And 1, 1 will become 1, 0 because it negates the second qubit from 1 to 0. These are on the so-called basis states, but for any general state, as we just said, it can be a superposition. Alpha 0, 0 plus beta 0, 1, gamma 1, 0 plus gamma delta 1, 1, right? A superposition of this. You apply the control NOT gates, then it's going to change it according to this rule. So 0, 0, 0, 1 won't change because the control qubit is 0. But the gamma, for the next two, because the first qubit is 1, then it's going to change to 1, 0 for 1, 1. So that's why delta is here. This is just a coefficient, a complex number. And then 1, 0 becomes 1, 1. So that is the control qubit. And we can use it to form entanglement, which we don't care in this talk. So now we know the quantum gate is just a laser pulse, right? So what is so special of them? Quantum gates, because they follow quantum mechanics, they are reversible, just Schrodinger equation, right? You can go forward in time, you can go backward in time. In classical computer, for example, if you tell me the output is 1 and the gate is NAND gate, I don't know whether the input is 0, 0, 0, 1 or 1, 0. But if you tell me it is control NOT and the output is 0, 1, I know for sure the input is 0, 1 because it's reversible. So a quantum circuit can be laid out like this. But what does it mean? This is the flow of time instead of space. So in a classical circuit, we put NOT gates, NAND gates, add the multiplexer from left to right. If you have 1 billion gates, you need to put 1 billion gates in your transistor chip, right? But no, here is just a passive qubit sitting there. And then you apply a laser pulse after some time, apply another laser pulse or microwave pulse, and you apply 1 trillion microwave pulse. The size of your qubit is the qubit chip. Your quantum chip is still the same. It doesn't change it. And that is the good thing about that. So if you heard about algorithms saying that they need 1 trillion pulses, don't worry that we need a very large area. And of course, they are reversible. You just need to apply a reverse operation, right? Until you do the measurement. Measurement will collapse the wave function, and then you will get 0 or 1. So that's the characteristic of quantum gate and circuit. Let's take a quick look on the entanglement example, right? So if I have 2 qubits, 0, 0, right? I can write it as 0, 0, right? I subscript it as A and B just to indicate that they belong to different qubits, 0, 0. I apply this Hadamard gate, which I just discussed earlier. You might miss it. What it does is that it's going to create superposition from a non-superposition qubit. For example, it was 0. You just trust me, it becomes 0 plus 1. We need to normalize it with 1 over square root 2. B is not changed because it doesn't get any gate. Again, this is just a laser pulse or microwave pulse, right? So from here to here, it becomes this. And you obey this distribution law, this linear algebra, we trust it now, then you will get 0, 0 plus 1, 0. Because 0 times to multiply to 0 and 1 multiply to 0, just distribution law. So this is a new state. Now, if we apply a control NOT gate to it, as we said, what does control NOT gate does? If the control qubit is 0, this is 0. Then do nothing to the second qubit. So it is still 0, 0. But if the control qubit is 1, apply a negation to it. So it becomes 1, 1, right? And then you become 1 over square root 0, 0, and 1, 1. And this is an entangled state. Why is entangled? Because whenever A is 0, B is 0. When you do the measurement, it's going to collapse to one of these two states. So it means that if you know A is 0, you know B must be 0, even you don't measure it. If you get A equal to 1, you know B equal to 1. So this is the so-called entanglement. Why I spend so much time on this? Because I was asked that maybe we should briefly talk about error correction. That's why I want to explain this control NOT gate. Now in classical computer, if you have tried to transmit some information 0 and 1, one very popular, although not efficient way is to do this repetition code, right? So I call you, or just when this team meeting doesn't work well, my internet is not good, I would just repeat saying, okay, I'm transmitting 0, 0, 0, 0. Okay, so you know that I'm talking about 0. Even one of them got flipped. I said 0, 1, 0. You heard 0, 1, 0. But since you hear more 0, you know by majority vote, I'm talking about 0. So this is a classical correction. But we cannot do this in quantum computing because to do this, we need to do copy, right? We need to copy. So, however, in quantum mechanics, there's a no-cloning theorem. You cannot copy any arbitrary state. And also, as I just mentioned earlier, when you measure a qubit, you will collapse to the basis state. So when you were in superposition, once you measure it for 1 qubit, you will collapse to either 1 or 0. So you actually don't know what was being transmitted. So this simple repetition code is not going to work. So what people do is to so-called syndrome measurement. So instead of really looking into the qubit, they try to entangle some auxiliary qubit with the real qubit. For example, psi is the real qubit. We entangle it with the auxiliary qubit. And here we use the C NOT gates, right, control NOT gates to do the entanglement. So this auxiliary qubit captures some information of this real qubit that we're interested in. And after the error channel, we do something to recover it. And that is called, that is one of the popular way to do this error correction. Of course, we will do something very simple here. Let's just look at an example. For example, here, I have this psi, right? It can be any state. It can be, it's one qubit, right? It can be alpha 0 plus beta 1. So again, it's a superposition of 0 and 1. I don't know what it is because I cannot measure. I entangle it with two ancillary qubits. So what does it do? So before I go into this entanglement system, I have a whole system. Now I have 3 qubits, right? So it is alpha 0, and then the other two are 0, 0. So it is alpha 0, 0, right? And then beta 1, 0, 0, because I treat it as the whole system. Now if I go through the first control NOT gate, what will happen? You will look at the control qubit. The control qubit is the qubit I'm trying to transfer. It is 0, so do nothing to the other qubit. But for the state that it is 1, it's going to apply NOT gate. I have two control NOT gate. This is control qubit, this is the target qubit. This is control qubit, this is the target qubit. So both of them becomes 1, 1, right? Then let's say we are so unlucky, we got a bit flip. It means that the whole system got flipped. And let's say only the first qubit got flipped due to some noise. So 0 becomes 1, 0 becomes 1 and 1 becomes 0. The other two qubits did not get flipped in this example, right? Then we can just do a measurement. But here we use a more simple circuit, is that we again use this control NOT gate to recover the state. So again, what do we do here? Because we have two control NOT gate, the first one is 1, so it is going to negate the next two qubits, so it becomes 1, 1, 1. For beta, the first one is 0, it's not going to do anything, so it becomes 0, 1, 1 like before. And finally, we have this circuit. You have not learned yet, but you can guess, is control NOT. This is just like control NOT. In control NOT, if your target qubit is 1, we flip it. Here means that if both of these control qubits are 1, then you flip it. So let's look at this, because now the control qubit are this ancillary qubit, so it is 1, 1. So you are going to flip alpha, right? So from 1, 1, so this 0 becomes 0. This 1 becomes 0. So 1, 1, 1 becomes 0, 1, 1. And same for beta part, it is 0, 1, 1 become 1, 0, 0. Now you see that through this circuit, we recover the original state, alpha 0, beta 1. But we mess up the ancillary qubit. And that is the idea. You always see that, very often see that, not just in error correction, but in other quantum algorithm. We need something called ancillary qubit to do some operation, to do measurement, to make the quantum computing successful, right? So in the future error corrector quantum computer, they will have more than this, because this only corrects the bit flip. Then how about phase flip and many other scenarios need to consider. But this gives a simple introduction. You can go through the exercise. In this channel, it might also flip this ancillary qubit, right? Then you should be able to correct them. And indeed, this one will correct it. So here you see one thing also. If you add more ancillary qubit, it doesn't mean that it is better, because each of them can get error also, and then your whole system will mess up. So these are the design constraints for quantum error correction. Okay, so with this basics, then let's look at the hardware. So DiVincenzo has 5 criteria about what can be used to make a quantum hardware. First, you need to have a well-characterized qubit. You need to have 2-level system, not 3-level, not 4-level. You need to be well-separated 2-level system to represent 0 and 1, and then there's superposition, right? You need to be able to initialize that. Here I will quickly talk about it. We'll not discuss later. One is thermal initialization. You just let it decay. If it is at the ground state, then it is at the ground state. And if it is at the excited state, you just wait for a long time, then it will decay to the ground state. Another is active initialization. You measure it. If it is ground state, do nothing. If it is in the excited state, which is 1, then you apply a pulse to it and bring it to the ground state. So that is initialization. This is not trivial because in many quantum algorithms, you need to do a lot of initialization. And if you need to take 1,000 seconds to do initialization, your quantum algorithm probably won't work. You need to have long decoherence time. You need to have a universal set of quantum gates, just like what we did in classical computer, right? For example, in classical computer, if you have a LAND gate, you are done. You can create any logic, right? Here you need to have many 1 qubit gates plus at least 1 entanglement gate that we just discussed. You also should be able to do specific measurement, because if your system force you to do measurement on all qubits, then many algorithms will not work. So these are the 5 criteria. So in the coming talks, I'm going to talk about the separation, how to form the 2-level system, and also how to implement the 1 qubit and 2 qubit gate, right? And sometimes you will see that there's a dilemma. If you have a long coherence times, usually you have a long gate time, and it's easy to understand. If you have long decoherence time, means you keep your state for a long time, means you don't interact with the outside world. Then of course it's difficult to control it. So you need to have a long gate time in order to change its state. So what is a quantum computer? In my opinion, at this stage, it's just a well-organized physics lab. You have many qubits, passive qubits sitting there. You apply a lot of laser pulse or microwave pulse to do initialization, manipulation, and selective readout. Of course, each qubit should have their level well characterized, and it should have a well-defined 2-level system, right? But it has noise, of course. So all you need to do is to have the right frequency, right shape, right amplitude, right phase, right time, right duration. So these are all what electrical engineers do, right? You can have different sets of universal gates. One of them is just rotation gates, 1 qubit gates that you can rotate about the broad sphere for any angle, plus a control NOT gate. Or this HST gate plus control NOT gate with some approximation. So in principle, if you can implement this, you will have a pretty good quantum computer. We talk about 2-level system, then of course we want it to be well separated. Unfortunately, they usually are not well separated. That's why we usually need to go to dilution refrigerator, to use dilution refrigerator or laser cooling to go to very low temperature. For example, here shows the qubit separation energy, and here shows the dilution refrigerator energy. That it is required to keep it to 2 level well separated, and we definitely cannot put it in the room temperature. Here shows the decay time. There are 2 types. One is T1, that you got flip, lose the energy. Another is T2, that is the characteristic time. You lose your phase. It was 1 plus 0, but then now you don't know what it is. It can be 0 minus 1 or 0 minus I1. So this is something we need to bear in mind. Okay, then let's talk about how silicon qubit is implemented, right? The diagram shows that the concept of implementing silicon qubit, when talk about silicon qubit, everyone is excited because we might be used the traditional semiconductor infrastructure for that. And ideally, if I can include all these control electronics, because they need to generate the pulses, right, as we said. And then we just have some transistor here with different gates, right? So here is a cross section under this with a plunger gate that try to lower the potential under it. This is just a transistor, but with single electron. That's it, right? And then we can have a barrier gate to adjust the barrier height so that we can let them interact to have 2 qubit gates, or to do charge transport for readout. But so it is very simple. In terms of the idea, is very simple. Use transistor, MOSFET, metal oxide semiconductor, to form a quantum well that is small enough to only confine 1 or 2 electrons, depending on the operation. And then we operate them, right? If it works, it is really highly integrated. So how can we have 2 levels? Probably you all know already. Spin. We can use the spin as to encode the signal. So without any external magnetic field, whether you spin up or spin down, doesn't matter. They have the same energy. If you apply an external magnetic field, for example, magnetic field pointing down, then the spin up will acquire lower energy, right? We're not going to go into the math. You just trust me. You know there will be a splitting of the energy. And that is called Siemens splitting. The energy difference is going to, you can correlate it to h bar omega. And omega is the qubit frequency that you will hear very often. So why qubit frequency is important? Because it's the distance between these 2 level systems. So how do we read out? How do I know whether it's spin up or spin down? So it's not easy. Here is not a good one. It's like a destructive one or a demolishing one, right? So how do we do that? For example, on this silicon chip, you might have a qubit in quantum dot. I'm not drawing the transistor, but there's a qubit here. Next to it, we put a quantum point contact transistor. And this is just a point contact transistor that its current depends on tunneling. And because it depends on tunneling, you know that just a little bit change in the potential, the current will change a lot, right? So if I have a charge next to it, you will have a smaller current if I have a negative charge. If I don't have the charge there, then I have a larger current, right? Because it will make the potential lower, so the tunneling of electron from one terminal to another terminal will be easier. And that's how we read out the spin. How? Through this so-called spin charge conversion. So this is the qubit, maybe the quantum dot. We store the qubit. We connect it to a reservoir. So because it's a very low temperature, so this is the Fermi level. Anything below the Fermi level in this reservoir, which is just a metal, right? You have a lot of electron. Above it, you don't have electron. Now, if you are spin down, which has a larger energy, then it has a chance to tunnel into the reservoir, right? Because this is empty state. And later, there may be an electron going back to the quantum dot. Now, when your quantum dot has this electron, then I have a small current. Now, in this quantum point contact transistor. But when you tunnel into this reservoir, I will have a spike of current. I will go up. But later, electron will fill back, right? Because it won't be able to fill the upper states because they don't have enough energy. But it can fill the lower state, right? But once it fill it, then that's it. Then this one will have higher potential again, then it will go down. So if we measure the current, and when it spin down, you will see a spike of current. Now, what if your state is spin up? Then you have a lower energy. Then you won't be able to tunnel to the electron reservoir because it's fully occupied under the Fermi level. So you don't see the spike. That's how you do this so-called spin to charge conversion. But every reading already remove your electron, right? You lose the previous electron. So you cannot measure it one more time. So this is not long demolishing, right? Quantum long demolition measurement that you hear later. We will talk about that in superconducting qubit. So we know how to read out the spin, right? How about quantum gate? A lot of math, but we don't need to worry about that. The only thing I want to mention is that a single qubit, as we said, is to rotate. Single qubit gate is to rotate the qubit on the Bloch sphere. So just do something to make it rotate, right? So we say that we can have this universal gate, but you can go to any point, just like Euler rotation, by doing free rotation. First about this z-axis, and then about this y-axis, and then about this z-axis. This can bring your qubit state from any point to any point you want, right? And this rotation can be implemented if you, in your Hamiltonian, remember we talked about the laser pulse or microwave pulse, they form the energy. We call it Hamiltonian of the system, right? Because your qubit will interact with the external field. So its energy will change. If you can have a sigma X, sigma Y, sigma Z, which we won't go into detail also, they are called matrixes. But the main point is that if you can implement this Hamiltonian, you will be able to rotate about these assets. And then you can realize the single qubit gate. So now the question is, how do we rotate? Okay, probably most of you know already, but if you don't, also not a big deal. The main point is that once we have the external magnetic field, we will form the two level. And at the same time, you have the so-called Larmor precession. Your electron state will precess, keep rotating about this Z axis. Okay, so this is good, but this is not how we control the qubit, but just learn the concept about Larmor precession. If you have a constant magnetic field, they will just precess about the direction of magnetic field. This is the same in classical magnetics. So how do I bring it from one place to another place? In reality, what we will do is that we have an external constant DC magnetic field. This can be pretty large magnetic field and difficult to flip over. At the same time, in the orthogonal direction, in this case in the X direction, we apply a sinusoidal magnetic field, which is a tiny one, small one, that we can change it. So it will point to the left and then point to the right, following this cosine function. But we will let it oscillate in the qubit frequency, which is the Larmor precession frequency, right? So we will do that. Then if you go through the math, you will find that you will start spinning down in this direction to any location you want. And that is the so-called rapid oscillation, right? Since we don't have time to go to the math, and probably you learned it before also, you just trust me, a constant DC magnetic field make you precess about the constant magnetic field. And then if you have a small rotating oscillating field, it will make it, when it is precessing, it will also keep going down and then going up to perform the so-called rapid oscillation. But this is the so-called electron spin resonance, when you have this one at the qubit frequency. But why is that? We can think a little bit more. So on the left, I'm showing the top view of the magnetic field, right? So this is the sinusoidal. You point very, very strong at the bottom, again weaker, and then pointing up and then strong. So this is sinusoidal. For sinusoidal field is equivalent to two vector rotating. This is rotating right, this is rotating left, right? For example, when two magnetic field is pointing in this direction, of course you get this strong one. Then when they are departing from each other, you get a weaker one, right? When you rotate, both of them are pointing in opposite direction of Y, you get 0, right? And this is equivalent. You can go through the math. Now, if we just stand on one of the rotating frame, for example, following this one, then we are changing the frame just like on merry-go-round. We are not on the left frame. We are on the rotating frame. Then the other one will rotate at an even higher frequency from us, because for this one rotating clockwise, we'll see the counterclockwise rotating at 2 omega L, right? And this is rotating so fast, we can ignore it because the FH effect is 0. Now, isn't that this is just like I have a constant magnetic field pointing in this rotating frame? And based on Larmor precession, isn't that if I have a constant magnetic field, then I'm going to have precession, precession about the rotating frame axis, right? And that is how we realize this rotation. And reality, we will work in this so-called rotating frame. So we will just like sitting on the merry-go-round, turn on this, and then we will be able to rotate it about the axis. And how do we implement in the chip, right? All we need to do is, first, of course, I need to have a constant magnetic field pointing in one direction. Now I'm not pointing down, it doesn't matter, this helps us define the axis. And then I have a wire next to the qubit running with the AC current. This AC current is going to have, just use the right hand rule, is going to have the circular magnetic field going around it. but it will keep changing direction and magnitude due to this oscillating current. And so the qubit at this point will feel a oscillating magnetic field which is perpendicular to this plane, right? Because at this point, it only feels the magnetic field at this point. And the magnetic field at this point is perpendicular to this plane, pointing up and down in an oscillating way. So with that, then we can implement the 1 qubit gate. How about 2 qubit gate? A lot of math actually, so we won't go into detail, but as I mentioned earlier, what you want is to have 2 gates. Sometimes you have the plunger gate, but here we don't have. You have 2 quantum dots, each of them has 1 qubit, and then here you have the barrier. The barrier will be brought to have some energy difference, and during this process, they will interact with each other. They go through the math, and we also will borrow the higher states of the system. Then you will find out that it can implement a control phase shift gate, okay, C phase gate. Now, this one doesn't look like a control NOT gate, but this is a result of the physics because the native gate of this system is a control phase shift gate, which is this one. But we can always add many other 1 qubit gates to make it a control NOT gate, right? So 0, 0 will give you this one if you add the superposition. But altogether, it's just to say that for different technology, you have a native gate or native 2 qubit gate or native entanglement gate because you can only construct it easily for the physics that it has. But we can always transform it to a control NOT gate. Okay, and here just show how we will do it, and it is very similar to the 1 qubit gate. Okay, so I'm done with the silicon qubit. Maybe a little bit fast, but we learned some basics, right? What we have just learned can be applied to superconducting qubit. I hope that you can contrast them and enhance your understanding. So we say we need to have a two-level system. Now in superconducting qubit, how do we do it? Actually, we can just looks like we can just have a LC tank, which are your expert, right? You are the expert of capacitor and inductor. When they resonate, they have a lot of energy. If you look at it, it means that they have a lot of photon, right? Because electromagnetic wave a photon. That's why I keep talking about photon in superconducting circuit. So you can keep cooling it down. You can lower its energy. Eventually have 3 photon, 1 photon, 0 photon. If you go through the quantization, like what we did for the simple harmonic oscillator in a classical mechanics, you will get to this type of quantization also. You have a ground state energy. When you only have 0 amount of photon, you actually still have a ground state energy due to uncertainty principle. And here is the solution of that. No need to go into details, but just want to show you that you have this flux of this system as the generalized momentum. As the generalized position, and the charge of this system as the generalized momentum. Because when your oscillator is oscillating, you transfer the flux, the magnetic energy to electrical energy, right? And then electrical and to magnetic energy. So the charge will increase and decrease, the flux will increase and decrease. This is just like a simple harmonic oscillator. The momentum will become 0, but the potential energy will be maximum. And then the potential energy becomes 0, the momentum will be maximum, right? So we can do this quantization, although we did not go to detail here, but I have that in my book. But so that is good. Isn't that we have a 2-level system already with 1 or 0 photon? But no, the problem is that they have equal spacing. And remember, what is a gate? Gate is to shine the microwave or laser pulse in here, microwave pulse, to bring it from one state to another. If you have equal spacing, means lack of anharmonicity. Then if a state was at 1, I shy a pulse, it may go to E2 or level 3 instead of going to level 1. Then the whole system failed because that is not my computation space, right? And that's why we use the so-called Josephson junction. I'm a little bit slow, so maybe I'll just skip the so-called Qubit pair. But basically, is that we cool down the metal to be a superconductor. When they're superconductor, they form the so-called Qubit pair, and they will become a boson. That means that they just like the photon. They can have the same phase and same state. So as a result, I can characterize the whole metal with one parameter, the phase and the amplitude in front. Because they share the same wave function, they become a macroscopic quantum object. With that, a Josephson junction is formed by a superconducting metal with insulator and superconducting metal. I just told you that because they are boson, so they have the same phase. So to describe this object, I only need to know the phase of its wave function, quantum mechanical wave function, phi A. And here is phi B. This is thin enough so they have interaction. So the difference of their phase will determine the current. That is Josephson junction, right? Equation. So the current actually is the sign of the phase difference, phi A minus phi B. And if you apply a voltage to it, constant voltage, you will get a change of the phi also. So think about this. If I have 0 voltage, phi is constant, then I have a constant current. That doesn't happen in normal life, right? You don't get current if you don't have voltage. But because it's superconducting, it never loses the energy. But if I apply a constant voltage, then the phi will keep changing linearly. Then the sign of a linear function is going to be oscillating. So by just applying constant voltage, then you will get an AC current, right? That's so special about Josephson junction. But more important is that because of this, you go through the definition of inductance, you can derive that their inductance is not linear. It depends on the phase difference of these two metals. And since it's not linear, then we can use it to replace the inductor in our LC tank. Also, because it's an inductor, so it has the so-called Josephson junction energy. These are all important when we design the circuit. So as we said, okay, then instead of just a regular inductor, let's just replace it by a Josephson junction. And now instead of this parabola, we will get this sinusoidal curve. And the separation between the first two energy will be different from the second two energy. And their difference is so-called the anharmonicity. So great. So we have two-level system, but it is useful to talk about what people usually use now. They use something called transmon. Transmon is just like I forgot to say, this is a charge qubit. It's just like the charge qubit we just said, but we shunt it with a large capacitor. The reason is this. If you look at the background noise, this is the background charge, right? You somehow get some noise or charge to the system. Here show the green one is the energy level of the second level. The orange one is the energy difference of the first and the first energy level difference. So E10, the 0 and the 1 state difference. If you have different background charge, you actually have different E10. Remember what's E10? That is the like the Siemens breathing, right? It is just the qubit energy. So if you have noise outside, then you're going to have your qubit frequency keep changing. Then you will lose all the information. And people find that if you shunt it with a large capacitor, then you will be pretty constant and insensitive to the background charge. Although you see the anharmonicity is decreased, however, it is still acceptable. So this is the so-called transmon qubit by having a Josephson junction in parallel with a large capacitor. So this one, we saw this slide before already, but I want to show this one more time to remind you that to implement a single qubit gate, we want to have a Hamiltonian that is of the Pauli matrix. And this, if you have, I can form a Hamiltonian, means energy landscape. With this sigma x, I will be able to rotate about x-axis. With sigma y, rotate about y-axis. With sigma z, rotate about z-axis. So why is that? So let's look at the 1 qubit gate for a transmon. So this is the transmon qubit. How do we do it? We just couple it to a microwave signal, right? So unlike the spin qubit, we need magnetic field. Now it's just electrical microwave pulse on the chip, right? So we will have an envelope S of t, and then with a certain frequency, omega 1. We are not going to derive it, but the main point is that after all the derivation, you will find that the Hamiltonian has a sigma z component, also a sigma y component. And remember, we say that if you have a sigma z, then you will rotate about z. You have sigma y rotates about y. But how fast does it rotate? It all depends on this phase, frequency, and also this omega r, which is the effective rapid frequency, right? But anyway, they all depends on what? S of t, which is the envelope. You shape your microwave pulse. Some constant, the capacitor you put there, coupling capacitor, the sum of the Josephson junction capacitor and the shunt capacitor, right? And this will help you to rotate it. So you see that in order to rotate the transmon qubit, not in our real 3D space, right? It is a quantum chip. We don't rotate it, but rotate the state. We can just use this one, right? But this is not good enough. We can use rotating frame approximation and rotating wave approximation, which we discussed earlier, right? So I won't go into detail, but what we're trying to do is that let's go to the rotating frame instead of the lab frame. And with that, I will be able to have both sigma x and sigma y. And then I have an I and Q in front of sigma x and sigma y. Now with this, you see that if I can control the value of I, control the value of Q, I will be able to rotate it about any axis that I want. So that would be cool, right? How do I will talk about how to control that later, right? So all our goal is that we need to form the Hamiltonian so that it has this form. And again, I already showed you, all this just depend on the circuit and microwave pulse parameter. How about 2 qubit gate? 2 qubit gates also pretty profound, but in a nutshell is that I have a Josephson junction on the left, a qubit 1 and qubit 2. And they are coupling through a capacitor. They have different qubit frequency, so they don't talk to each other, right? They have just like radio. They don't have the same channel. When I want to do the 2 qubit gate, one of them, I will change the qubit frequency of one of them. And I did not talk about how to change it so far. Actually, some Josephson junction are flux controllable. We change the magnetic flux outside from it, then it will change its qubit frequency. Once the qubit frequency resonance, then they will go through the math. You will find that they will start having this Hamiltonian. And if just turn on it for the right time, you will get something called I swap gate. So again, you're not C-phase gate, not C-naught gate, but I swap. Just because of the physics, for superconducting qubit, I swap gate is the best, right? And again, just go through at different number of 1 qubit gates with 2 I swap gates, we can make a C-naught gate. And so now we all know how the qubit work, right? Then let's look at the whole system. Superconducting qubit reside here. The rest are classical. You send the signal full programming, full attenuator to here. You manipulate the qubit, or you also can read out the qubit. If you want to read out the pulse, we'll go through here and go through an amplification train. So let's look at how do you do 1 qubit gate? We say that we want to form this Hamiltonian, right? So maybe this line is not that important. Basically, eventually, I want to have an I port in phase and quadrature port. They just send out different type of pulse, and then they will bring to higher frequency through a mixer to generate this signal. Then I get the 1 qubit gate. But again, they all controlled by how much I put from these two output ports. How about readout circuit? For example, in this circuit, I just say that we'll send a readout pulse, and then you will go through a resonator, and then we detect it. Now, if this is a resonant frequency, then everything will go through, right? Otherwise, if the frequency, this one is off, is different from my signal's frequency, then the S21 will be very small. The way we read out a qubit is that we couple the qubit to this resonator. When qubit is at one state, it's going to change the resonator to another frequency. When it is at zero state, it will change to yet another frequency. That is how it works. For example, originally the resonator frequency might be at omega r. If my qubit is an excited state, then this will be the S21. And if I'm at the ground state, it will be the this one, will be the green one. By looking at the magnitude, we cannot distinguish them. But we can look at the phase. You will find that they have different phase, right? Here, plot the imaginary part and the real part. For example, you see that they have the same imaginary part, but the real part, one is positive and one is negative. And that is the so-called dispersive shift of resonator frequency. So by plotting on this imaginary and real plane and do some transformation, if there's no noise, I will be able to distinguish them. And actually, I should only have two dots. But when there is noise, I will have a big circle, right? And that's why you need to make the separation large enough. Otherwise, they may merge, and then you cannot distinguish 0 or 1. So that is the how you read a superconducting qubit. After you read out, you need to demodulate. This is the circuit. I will skip it, but basically based on the signal you get, you just reverse the process, bring it from high frequency to low frequency, filter up some, and then through the low pass filter, then you can get the phase. As I said, what we need is the phase, right? So once we get the phase, we know whether it is 0 or 1. I know I only have 9 minutes. I will skip the amplification train part, right? Because of time. I will also quickly just show you what a quantum chip look like. So for example, this is a chip with design. This is the fit 9, right? You put in the manipulation pulse, or you put in the readout pulse. Let's look at the readout pulse. The pulse will come here, and you couple to a resonator. This resonator is further coupled to the qubit. So when the qubit state is changed, then the resonant frequency of this resonator will change. As a result, I will get different S21. So very often we share 2 qubits or even more qubits on the same line to save the space. But we need to make them to have different frequency. So this is like frequency multiplexing. You can think in this way. Some qubit, we make it flux tunable, so we can change the frequency, right? Here, this qubit, we did not. And just in case you don't know, if you look into the qubit, this is the Josephson junction. You don't see it, but then you have this shunt capacitor, right? And these are the ground plane, and this is the waveguide. You do a cut, then you see the niobium. They are in the order of 150 nanometer. So we already say that to design the superconducting qubit is all circuit parameters, right? So here a little bit busy, but we won't go into detail, but we just want to show you that, for example, the charge energy, the capacitive energy, which would determine the anharmonicity. We say anharmonicity is very important. We need to have different separation from the first and second level, right? So anharmonicity, we can change the capacitor, right? So it depends on this. We might also want to change the, then we use the Josephson energy to change the qubit frequency. If we have many qubit, we need to have different frequency, as we said earlier, so that it won't get, so that we can do frequency multiplexing, right? And it depends on the critical current, etc., right? And we also need to make sure that the so-called normal resistance is within the fabrication range, because this determines the so-called critical current. So by using all these circuit parameter, we just do the right thing and we use HFSS to do the simulation to figure out what is the capacitance of the pair, what is the inductance. Actually, we cannot do inductance, we just put it there. Because for the tooth we are using, it cannot simulate Josephson junction, we just put an effective inductance, but you will calculate to get the eigenmole and quality factor, etc. Right. So that's one thing also to so-called the energy participation ratio, which is going to affect this separation of the readout, the cross curve. And there's a method to do the so-called energy participation ratio simulation using HFSS. And won't go into detail, but the point is you convert the quantum mechanical thing to classical simulation. Right? So HFSS is very important in doing superconducting qubit measurement design. And here are some video I make to help people to do the design, to use the tool. I only have 5 minutes. Let me just very quickly talk about, we do have this cryogenic measurement capability. We have RF, 2 RF Pro and 4 DC Pro. Pro DC Pro go to about 2 gigahertz. And here show a measurement of a 65 nanometer chip. We have a test chip and we probe them. We have a few devices to get some statistics. Here show the CV measurement. IV measurement, definitely you see that the subthreshold slope is very deep when you go to 4.2 Kelvin, right? This is for PMOS, but the main message is here, actually we don't see much difference between 300 Kelvin and 4.5 Kelvin. If you look at the temperature here, if you look at the, for analog application, right? The GM actually increase, but out reduce. As a result, GM out is almost constant. Right? Similarly for the PMOS. So there's not much change. And that's why some people, they just use their design directly for at 4 Kelvin and it works well. It's because of this. We also study the variability. We see more variability when you go to lower temperature, probably due to more impurity scattering. What we're showing here is 65 nanometers, so it is still heavily doped in the channel. Right? We developed some empirical equations to help people to gauge how each different parameter, GM, ion, will change as a function of temperature. Right. Here we also show that we use room temperature measurement to study some properties. For example, the scattering of electron under the gate oxide can be due to photon scattering, surface reference scattering, and Coulomb scattering. Sometimes it's very difficult to disentangle them. So if we bring it to 4 Kelvin, we can create like this the mobility extracted as a function of electric field. At lower temperature, of course, the photon scattering effect will be gone. So then you can see that for these two devices, one is called regular, one is MST. MST have much higher mobility than this one, and that's why we say the surface rough scattering is much better in this process. And we use this to extract the parameters. Right. We also did other study, including using FinFET, just to show you we do have this, but have not published yet.